All right, we will start. There's still folks coming in, and they'll probably coming in throughout the start of the session. But welcome to session 11A, Tools and Datasets, part 5. First, a reminder that we have a code of conduct. The conference has been a wonderful environment. So just continue to be inclusive, respectful, gracious, be very interactive. But if there is any problem, please notify the organizers immediately. So for this session, we will start with a highlights talk of 20 minutes. Then we will have 4 excellent 12-minute talks, and we'll have short transitions between the talk, likely time for one question. And we will have about 5 minutes at the end of the talk for a few follow-up questions. So it's a packed session. So please use Slack. Hopefully you're all looking at Slack channel 8, Tools and Datasets. And I will be looking at Slack for one question at the end of the talks, and I'll pick some of the best question or the most relevant question at the end of the talk. So for this session, we will start with a highlight talk, recommending us to consider a AI to predict I don't know, which is great and helps characterize uncertainty. We'll follow with 4 talks, including AI-based access to NEPA data, a method to quantify the shape and textural information present in images, anomaly detection for extreme events, use of dynamic mode decomposition to make decadal forecasts. So much to look forward to. The first talk is from Elizabeth Barnes at Colorado State, and take it over, Elizabeth.
Okay, how does that look?
Looks great.
Good to go. All right, thank you everybody for joining me this afternoon. I'm going to talk to you about what we call controlled abstention networks. And the whole idea here is neural networks that say, I don't know, to learn better. All right, so let's get going here. What's the motivation? So my background is climate science. I'm a climate dynamicist. And at least in the world I live in, the Earth system is incredibly complicated and chaotic, and making predictions is really, really hard. And so one thing we come to terms with is the fact that we just cannot make perfect predictions all of the time, be it at the weather time scale all the way out to decadal and beyond. So the idea, this is sort of the motivating problem. So the whole idea here is what we call the abstention loss, works by incorporating uncertainty into the neural network's prediction in order to identify the more confident samples and abstain, that is, say, I don't know, on the less confident samples. So it's applied during training rather than post-training. So it's applied while the network's training. And the idea is that it will preferentially learn from the more confident samples. So here's the general idea, is what we're going to start with is some data set where the network is going to try to estimate the uncertainty of each prediction during training. Then it will have a loss function that learns to identify the more confident predictions and then attempt to learn them better than the less confident ones. And then an important piece is to compare how it does to some baseline method that didn't have this abstention, because if the abstention doesn't help us, then why make it more complicated? A point of this slide is to show we've actually have this is based on work of 2 papers. We have a classification paper and a regression paper. Today, I'm going to talk more about regression since that is often very applicable in geoscience, but also because I think it's something that didn't really exist as easily beforehand. And finally, I just want to point out in the upper left-hand corner that this work is heavily informed by a PhD dissertation out of the University of Washington just this past year. Okay, so step 1 is we have to find a way to add uncertainty to our predictions in order to then use that uncertainty to learn the more certain better. Okay, so uncertainty for regression tasks. Imagine we have some data set where we have the X on the X-axis and then the label or the Y on the Y-axis, and this is a regression problem. We want the neural network to make a prediction and estimate its uncertainty. And as you can see here with this data set, there are some X ranges where the Y is relatively constrained and other ranges where that spread or the possibilities of Y is quite large. So what we want to do is go in, and if we look at this spread for one particular X value or range of X sliver, if you will, of X values, we want to be able to predict, say, a Gaussian distribution. So actually predict the conditional distribution of Y. In this case, it's a Gaussian. I've drawn that here in blue, where the true y is shown in pink. I will point out it does not need to be a normal distribution, does not have to be a Gaussian, and we have a write-up discussing other alternatives and how to implement them. So we train a neural network to try and estimate this uncertainty. And here's what it does, and then I'll tell you how we do it. The idea is now these blue vertical lines are the network's prediction of that conditional probability distribution. So it's guessing how sort of up and down, how tall that distribution should be. And you can see the network is adequately learning that it's more confident, that is skinnier conditional probability distributions in some regions and wider in others. So it's doing an okay job here. So how do we do this? The idea here to get this prediction of this normal distribution in this case is you might think of typical regression problems looking something like this. You have some input layer into your network, a bunch of hidden layers, and then you output a y value, right? The label, the regression problem you're trying to predict. Well, instead of predicting the y, we instead predict two values, and these are the parameters for the particular distribution that we've chosen, in this case, a Gaussian. That is, we have the network predict the mean and the standard deviation of that conditional distribution. Now, once it makes those predictions, the loss function we use, so how we train the network to do a better job at predicting that mu and that sigma, is we use just the negative log p, where p is that predicted Gaussian evaluated at the true label y. Now, this is how this works. This is also, by the way, directly related to maximum likelihood estimation, if you're familiar with that. But in picture form, here's what it looks like. So the network has guessed some distribution. So I look at panel A here. It guesses the blue distribution for a particular sample, and that's based on mu and sigma. What we do is we go and we draw a vertical line where the true y value actually was. And P is defined by where that line hits that probability distribution. So in this case, it's a very small number for A because our network's overconfident. It was really confident and it got it wrong, or it wasn't close to the true. In panel B, instead, the network's super underconfident, right? It spreads everything out. But if that's the case, when we look at where the true value of y lies, our P is also a small number. And by the way, again, this is the P value that goes into that loss function. It's not until panel C, the network has to get a good idea for how wide that distribution should be. It shouldn't be too wide or too narrow, that it maximizes that P value when we actually evaluate the distribution at the truth. In this way, using this loss function, the network will actually learn to correctly predict mu and sigma of this underlying Gaussian distribution. So now we move on to the baseline approach. All we've done so far is describe how we can possibly add uncertainty in a simple way to a network regression task. So here's our baseline approach. And what I mean by that is this is what we're going to compare our abstention approach to see if it adds value. So we've trained a network to input a sample and predict some conditional distribution for y. So here it is again, a Gaussian with a sigma and a mu. Well, if we have a lot of samples, it's making a lot of predictions of different conditional distributions. Some are, less certain, some are more certain. And that is the skinnier they are, the more certain the network is. Now, once we have this long list of samples and their predictions, we can just say, well, hold on, we already have some uncertainty associated with our predictions already. Let's just only keep the certain ones. Let's only keep the samples, a certain percentage of samples that the network is really confident on, and evaluate how well it's doing. So that is, we're only going to keep the X% most certain samples. Now, if we just do that and evaluate our accuracy, this is already a very powerful approach for estimating uncertainty and for using it to identify samples that we might be more confident in. And in this way, this is what we're going to use to compare our abstention network to. All right, so now for abstention during training. I haven't said anything about abstention yet, other than throwing out the samples where the network's not very sure of itself. So what do I mean by abstention? Well, this is this idea of training the network to guess I don't know. All right, so here's all the abstention loss works. It's quite similar actually for regression and classification, but we're only going to talk about regression quickly here. So what you'll see is, once again, we have our loss function, L, and you see that log P hiding in there. So that's the same log P we had before, but now we have an extra factor Q on the front end of it, and this extra term here on the right, which in essence penalizes the network for abstaining too often or saying, I don't know. Otherwise, the network will just say, I don't know all the time, right? Just to reduce the loss. So the way to think about this, again, is this Q is some prediction weight. This value of alpha controls how much it abstains or says, I don't know. And then there's a data specific scale here that I'm not going to go into details that helps determine that particular prediction weight. All right, so what ends up happening is this alpha value is the value that allows us to control how many samples the network abstains on or says, I don't know, during training. So here's an example where epoch is on the x-axis and the y-axis shows how many samples the network abstains on. And as you can see, as the network learns, it starts to hover around this abstention set point of about 70%. And that's because as the user, I told it, I want you to abstain about 70% of the time. That is, I want you to focus on the 30% most confident samples while you're learning to attempt to learn them a little bit better. So you can see how it does that here. All right, so this is all sort of ideas, but what does this mean in practice? And I find that up until now, throwing equations at you probably isn't terribly helpful. So let's show you an example. So here's a silly example, but I find it really enlightening. We have a bunch of data points here where our X is our input and we want to predict Y, so we can visualize it. 80% of these dots are in that point cloud, all right, which is sort of a messy blob. So most of our data, and this is the big point, most of our data is noisy and in a blob. Only 20% of the data lies along a beautiful linear line. What we'd like our network to do is identify the 20% of the data points that lie along the line and learn to abstain and just not even worry about the cloudy points. All right, so we do that. We train our abstention network. And in fact, in this scenario, actually, we also have an option to have the network choose how often to abstain rather than the user choose it. And in this case, the network actually chooses to abstain on about 20% of the data, which, as you can see on the left, is exactly how much data it should have guessed in the first place. Furthermore, it learns that line incredibly well and learns not to predict the cloudy points because those are less certain. Now we have to compare this to a baseline approach, which, as I said, does this add anything? So that's what this shows. So the way to read this plot is the error of the predictions on the y-axis, and the x-axis is how often the network throws out the data and says, I don't know on these, because we have to compare apples to apples, because with our baseline approach, we choose how many samples to evaluate. And in the abstention network, in this case, it chose how many samples to abstain on. The big point here is as you abstain on more and more, you do better and better. That makes sense. You're in essence weeding out the samples you're not sure about. But the big point here is that the abstention network does better than this baseline approach. That is, because it abstains during training, it actually learns the more predictable samples better. Okay, this is a 1D simple example. This is not typically what we try to actually predict. If it was, we would just look at our data, and as a scientist, we'd say, I'm going to draw a line over there. So let's go to a more complex example. In this case, we're going to use a data set, a synthetic climate data set developed by Dr. Antonios Mamalakis, where each input sample is a global map of synthetic sea surface temperature anomalies. What he does with these maps is he pushes them through a nonlinear function that he's determined, so he knows that function exactly. That ends up being a nonlinear sum of those values over the map. And ultimately, then each of those samples is associated with a Y value or a label. So this function that connects this map of sea surface temperatures to a Y label is known. Antonios came up with it, good. And our goal here is to task a network with predicting what that Y value is. But really what I'm going to do here is, since this is a synthetic data set, I'm going to turn it into predicting the underlying distribution of the Ys, because there can be a potential range. Now, the way Antonia set up this data set, it's perfectly known this connection between the input and the output. But my point is some samples are noisier than others. So I'm going to go in and actually add noise to the data. So then we can see how the abstention network does. So what I'm going to do is I'm going to draw a box in the El Nino region. And whenever that average sea surface temperature is above, say, 0.5, I'm going to leave the sample as it is. All of the other samples, I'm going to shuffle their labels around so there's no connection between the input and the output. Put another way, 29% of these labels or these samples are untouched when there's a strong El Nino, and all of the others just have noise. So the network needs to learn to identify the El Nino samples as confident ones that it knows, and then learn that relationship between the map and the output. So we do this, and we do it also for our baseline approach, and we can compare the errors in the ultimate prediction. And the whole point here is that when you look around 30%, which was the correct percentage of samples that were not corrupt, we see that once again, the dots, which is the abstention network, do significantly better than the baseline approach, suggesting that it's learned those relationships better because it wasn't being distracted by the noisy samples. So I don't have time to go into other examples, but in the paper, we talk about this can be used to identify corrupted inputs. It can be used to look at forecasts of opportunity, like I just showed. In other cases, we can show how it can be used to identify arbitrary labeled noise, as well as structured noise. So if you're interested in this, we do have two papers. One, as I said, on the regression setup, the other on the classification setup. They're both on archive and currently going through review in James, if you're interested. And then finally, I will point out that we just, as of yesterday, got a guide up on archive on how to incorporate uncertainty into neural network regression tasks. For example, I mentioned that you don't have to assume a normal distribution for your conditional probability distribution. In our case, actually, we argue for this wonderful family of distributions that under certain conditions can become a normal, but if your data has, if you expect skewness in one direction or the other, it can account for that as well. And in this case, instead of predicting mu and sigma, only 2 parameters of a distribution, you predict the 4 parameters of this family of distributions. All right, so in conclusion, I have 3 real take-home ideas here. The first, predicting the local parameters of a probability distribution is a simple way to add uncertainty to regression tasks. Forget abstention. This is already a really simple way to do this. And I haven't mentioned it, but it will work for most any neural network architecture, because all it needs is to modify the loss and the number of outputs. It doesn't really matter what the architecture itself on the inside is. Secondly, the abstention loss for regression and for classification allows the networks to identify opportunities for skillful prediction and then learn them better during training. And as I guess I just said it here, implementation of the abstention loss is straightforward in most network architectures. So with that, I will just flash this up in case anybody wants to take a screenshot of some of the references, and then I will get back to conclusions for questions. Thank you.
Thank you, Elizabeth. Great talks and excellent incentives. I think all of us using neural nets, I think, are just looking forward to try this. So I have a couple of questions from Slack, one that has been voting up, and it's a question about extreme events. Is there the potential that you would discard extreme events which are relevant and important? How does that work?
Yeah, absolutely. If they're practically unpredictable, or the network's going, these are confusing me, I'm trying to learn something else, then yes, it will not learn those samples. So this is not a solution for everybody by any means. This was motivated by the idea that some samples, just due to, say, chaos, are going to be noisy, and they're getting in the way of the network finding the relationships that are predictable. So in that sense, if you're interested in the extremes themselves, I wouldn't use this setup and feed it all possible data. I would probably instead wonder, which extremes are predictable and which extremes just were sort of unlucky black swans or something. So then you need to intelligently set up your data set. So maybe it's only made up of the extremes.
Yeah, thank you. So if your abstention network was to predict extreme event, would you be able to say that that you can do a little bit of extrapolation with a neural net? Is it a potential safeguard to predict extreme events or not?
Oh, so what do you mean by that? Sorry, what do you mean a safeguard? Oh, if it was able to do it, then it means that they're confident?
Yes.
Oh, I mean, yeah, that'd be awesome. And in some cases, the extremes are what you can predict. So if you think about climate teleconnections, when it's a strong El Nino or a really strong La Nina, you expect that signal to be larger. And so potentially this abstention network will identify those samples as the ones to keep. Whereas when it's sort of ENSO neutral, it wants to ignore them because lots of other things can happen.
And one more question from Slack, from Lander van Hoef. Is the true probability distribution around data points in the training data a required input, or can this work when quality of training data points is not known a priori?
Yeah, so no, you do not need to know the probability distribution beforehand. If you did, part of me is like, you've done half the hard work already. So that's part of our motivation for this family of distributions. Let's say you think your data is probably not normal. This is, to be clear, this is not the data itself, but sort of the range of uncertainty around those, for a particular sliver of inputs. That's why I like this family of distributions, because if it is normal, it will just predict certain parameters to be 0 or 1. And if it's not normal, it will allow for skewness. So in this way, you do not need to know what your distribution was ahead of time.
Great, thank you, Elizabeth. And there's another question from Roy in the Slack, but we're going to move to our next talk from Sudha Ram at the University of Arizona. Take it away, Sudha.
Okay, let me share my screen here. So can you all see it?
Yes, working well.
Okay, wonderful. All right. So in this work, I'm going to be talking about some AI methods, machine learning methods and tools we're building for environmental impact assessment. And there's a large team, and I'll talk about the team at the very end. So what is environmental impact assessment? In 1969, NEPA, the National Environmental Policy Act, was created as a new approach to environmental governance. And it had a very elegant vision of using science and also involving public participation for evaluating projects that might have potential environmental impacts, and also making better decisions from a participatory kind of view. So what does that mean? So what NEPA requires is anytime there is some sort of a federal action that might potentially have environmental consequences, that project has to go through an environmental impact assessment, and that process is very complicated. And so you don't have to really read this busy slide other than seeing that there's a bunch of steps involved, and each step has a yes or no decision, and there's a document that's created, and these documents are fairly complex. And in some of these steps of that environmental assessment, there is a public scoping and a comments period, and you have to make sure that public comments are reflected, and the draft statement is created, and the final impact statement is created. And then finally, there's a record of decision. So there's all kinds of documents that are created. Now, this process is exceedingly complex, and on an average over the last 50 years, if you look at the number of documents that have been created, there's in excess of 37,000 EISs containing essential knowledge, and they're scattered across a lot of different federal agencies. And so our project was intended to create a knowledge platform that would make these documents accessible and also incorporate AI methods so that we're able to make this process more efficient and be able to address the needs of various stakeholders. So what I'm going to do in the next several minutes is basically show you a snippet of what our system looks like and talk about two ongoing pieces of work that incorporate state-of-the-art AI methods. So the first one that I'm going to talk about is basically what the system looks like. And we actually have a working system called NEPACCESS. And I used an example that's relevant to NOAA, where you can search for these documents. So I use the example of marine sanctuaries. And some of these documents are available on other websites like the EPA's search system or HathiTrust or others. But in our system, what you can do is using some sophisticated natural language processing techniques. We don't actually have to use the exact words of marine and sanctuary and NOAA. Instead, we can use other words that are similar, and that still gives you a list of results that are relevant to looking for EISs related to marine sanctuaries. And so with NEPACCESS, you can see we get far more results that are relevant. So our recall and precision is much better than any of these other websites. And if you look at the EPA websites, these are some of the EISs that are very relevant to marine sanctuaries, but those don't get retrieved in these other systems because our search techniques use word embedding methods, as well as we're able to automatically link various documents to each other, even though their titles are not similar, their descriptions are not similar. We're able to link the draft and the final and the record of decision to each other. So it kind of shows you all these documents in a very systematic manner. So that's where the system is right now, but I'm going to talk about two aspects of our system where we want to enhance the NLP techniques. One is when you look at the EIS process, often it takes on an average about 4.5 years to do an environmental impact assessment. Some projects take more than 10 years, some take fewer years. There are very few projects that can be completed in a year or less. And when one of these projects comes in, there's a lot of complexity involved. There's usually a lead agency, there's cooperating agencies. And so creating these documents and assessments is a very complex process, as you saw from my second slide. So one of the things that's really important is predicting time to completion for an environmental impact assessment. And the other thing is to make sure that public comments are actually being considered properly when we do go from the draft to the final EIS statement. So I'll go through each of these one by one in a couple of minutes each. Why is predicting time to completion important? Because if the agencies that are working together on an EIA understand how long it's going to take, they can allocate their resources much better. They can manage multiple processes, and corporations can plan ahead on related undertakings. And as you saw, there's multiple stakeholders involved, such as there's usually a lead agency, and there's cooperative agencies, and then there's, of course, public that's involved. And all of these relationships actually impact the time to completion. And so using simple machine learning models actually requires feature engineering and does not account for these types of relationships between stakeholders. So we've proposed a graph representation learning method that uses graph convolutional methods. It uses a role theoretic approach to actually construct the graph first and analyze relationships among the various EIA stakeholders and represent it as a heterogeneous network. And then it uses a neighborhood aggregation method to understand how these various nodes of agencies, locations, lead agency versus cooperating agencies are all embedded in a multidimensional space. And furthermore, we apply different convolutional operations across different types of edges. We also take into account different aspects of node properties, which is instead of randomly initializing node attributes in our graph learning approach, information describing each node, such as the title with keywords in it or different words in it, are then used to obtain word representations of tokens included in each document. And we train a word embedding model such as word2vec, and these are combined to generate higher level representations of the documents. And these provide additional information into our learner. And we use a custom loss function then to eventually predict how much time it's going to take to actually complete an EIA process. And so we've compared our method with other methods, such as the standard machine learning methods. And you can see that our errors are considerably smaller when compared to these other methods. So that's all I'm going to say about this particular aspect. The second part of our AI methods inclusion in NEPACCESS is stance detection. Stance detection is a very important part of public participation, is a very important part of the EIA outcomes. And so when a draft EIS is created, the public has an opportunity to participate, and then understanding what the stance is of the public in this process and making sure that their concerns are actually incorporated into the final EIS is very important. Stance detection is different from sentiment analysis in that these opinions have to be analyzed with regard to specific targets. And one of the big challenges is that there's very little data available. So we use a transfer learning method where we use data sets from other types of projects where there has been a ground truth for stance detection. And we incorporate that into a word embedding model, which then weeds out the irrelevant comments and then uses a bidirectional LSTM, which we've compared with a multi-layer perceptron to actually classify the stance into positive or negative or neutral. We still have a long way to go in terms of overall accuracy, but you can see that our bidirectional LSTM, or recurrent neural network with transfer learning, works very well in terms of recall for negative comments. It works much better than the other methods for precision, and overall it improves the accuracy. So in summary, what we want to do is now take these methods and improve on them and incorporate them into the NEPACCESS system. We also want to incorporate a map-based interface and then use these methods to do cumulative impacts of different projects. This is a complex interdisciplinary project, and you can see the PIs. It's an NSF supported project. And if you have questions, if we have time, I'm happy to answer them. And this is my contact address.
Thank you very much, Sudha, for a great talk and a great resource. Lander, why don't you load your presentation? And Sudha, a quick question. Is there an API to access that programmatically? And if so, can you put it in Slack?
An API to access all the documents in our repository?
Yes.
Currently, we don't have an API. We do allow you to download the documents, but we're working on generating that API.
Great. Thank you, Sudha. And so Lander for Hoef, just take it away.
Cool. Thank you very much. Yeah, welcome. So this is an introduction to topological data analysis in general for remote sensing. And so the big thing that I want to say even before we get started here that I'm hoping to get out of this is I'm really excited to see what other applications this tool can have. So if you're watching along here and see something, you're like, oh, I could totally use this. Please let me know. I'd be so excited to hear about it. So let's start with what is homology? So for the purposes of this, homology is a mathematical tool that lets us capture topological properties about the shape of some object. In particular, homology is a way of counting the number of holes in every dimension, as well as the number of connected components. And what do I mean by holes in different dimensions? Well, a one-dimensional hole would be what we have in this upper right example, where we have something contained in a circle, where a two-dimensional hole would be something contained in a three-dimensional void, or inside a two-dimensional sphere, like we have in the lower right here. And as a note, homology is something that can be computed quickly and efficiently. So this is not just a theoretical mathematical tool, but it's actually computable. So let's get to the second half of this. What is the sublevel set persistence part? So the sublevel sets that I'm referring to is, suppose we have some three-dimensional surface. Maybe it's an actual surface, maybe it's intensity data in a grayscale image. And we form sublevel sets by taking a plane and scaling it up through our data and including all of the pixels or regions of that surface that fall underneath that level. So the sub-level set, which in the animation here, we see our surface and we see the level rising through it on the left. And then in the middle here, we see an illustration of the actual sub-level sets themselves, the pixels being included at every level. As a note, the choice of sub-level set rising from the bottom is quite arbitrary. There are many applications where you want to talk about super level sets coming down from the top and including everything above, and that works perfectly well as well. And so at each of these sub-level sets, what we do then is we compute the homology of the sub-level set. So at every one of these images in the center, we're computing the homology of that and recording the output. So how many connected components are there at any given intensity level? How many holes are there? And we record that information into this barcode out on the right here. And the way to read this is each red bar represents a connected component, and the X value at which that bar begins is the intensity level at which that feature shows up. So these two little red bars are these small connected components that appear in the top corners of this image. And the bar stops when that feature gets merged into something else. Either a red bar stops because the connected component merges with something else, or a blue bar representing a one-dimensional hole gets filled in. And so we say that that feature dies. So in this way, this barcode can contain information about connected components that are appearing and disappearing, and holes that are appearing and disappearing as the texture of this surface throughout intensity. I should note this is not the only way of viewing these data. The barcode on the left here is what I just explained. The persistence diagram on the right is an alternate way of viewing the same set of data. That uncovers different features and can be more useful for some applications. So I wanted to present both of these because they're both widely used in literature. So where has this been used before? Because surprise, surprise, we are not the first people to be using this for science or even remote sensing. So it's been used in neuroscience to distinguish brain scans of people with and without autism. It's been used to detect Kolmogorov flow in fluid dynamics. It's been used to evaluate the severity of prostate cancers. It's been used to detect atmospheric rivers, identify active wildfires, and to quantify the diurnal cycle in hurricanes, which that's the image on the right here is from a paper doing that. So the data I mostly work with is satellite imagery of clouds. So this is GOES-R imagery, band 2, and on the left here, we can see a 28 by 28 patch, and the green regions are the super level sets because that's what makes the most sense for this application, sort of filling in and spreading out. And here we can see the barcode and the persistence diagram. And unsurprisingly, when you start working with real world data, it's not nearly as nice and neat as the contrived example that I used in the previous animation. So that's showing up here. Now, the big question is like, okay, great, here's this tool. What can it actually do? What can it detect? So here's an example of the sorts of things that this can look at. So these images are from choosing one particular property of these topological barcodes, and taking a whole bunch of images and just sorting them based on the value of that property. And for this example, that the property I used was the average length of a red bar. So all we're looking at here is connected components and over what intensity range do those stick around for on average. Are the connected components short-lived, so they join into other components very quickly on average, or do they persist very strongly? And as we can see, if we look at the minimum over on the left here, we get this very smooth image with really very few features at all. And then as we move up the quartiles up to the maximum all the way on the right, we get this very highly textured image with a lot of small, distinct, but like high relief features in it. So that's the sort of thing that this is being able to pick up. And so one of the key strengths of this that I want to highlight is that this is really looking at this is not pixel by pixel information. This is looking at how the data are arranged relative to each other and doing that in a deterministic way. So this is a straightforward algorithm that if you run it 100 times, you'll get exactly the same results. So it's very predictable and interpretable and explainable. So finally, this is just a slide from some stuff I've been working on to use this with recently. I've been working with some data from the sugar, flowers, fish, and gravel data set, which is a huge data set of hand-labeled cloud images. And so I have an algorithm that looks at these annotations, draws subsamples. So all the algorithm is looking at are these the regions in the little white boxes, and then computing pairwise distances and doing an embedding into 2D using multidimensional scaling. And the resulting plot for a subset of these samples is put here, with the colors being from the original labels in the data set. For on the left, the cloud type called sugar, which is representative images on the left, and then the flowers on the right. So to a human, clearly different textures, and just using these barcodes, the algorithm is able to separate these relatively well. Thank you. So I'm mostly just interested in sharing that this tool for looking at texture exists, and I'm really interested in finding out more about other environmental science and remote sensing applications that we can start using it on. Thank you very much.
Super. Thank you. So yeah, and anyone get in touch with Lander there. If you have a data set, I'm sure he's going to be ready to help you test his method. I have one question on Slack from Eduardo Rodrigues. For remote sensing, is there any application of homology for large number of dimensions, larger than 2 or 3?
Yeah, so certainly if there is a data set that naturally lends itself to that is higher dimensional, you can do sublevel set homology and uncover higher and higher dimensional holes. There's no reason to stop at 0 or 1 dimensional holes. Those are just the ones that show up in image data that I've been looking at. But absolutely, as you get to higher and higher dimensions, homology becomes somewhat less efficient to compute. But for certainly 4 or 5 dimensional data, there's no reason this couldn't be used.
All right, super, thank you. So we're going to move to the Delores Knipp talk. So please load, and thank you, Lander, for your talk. Great talk.
Thank you.
And keep on interacting over Slack. We don't have enough activity presently there. Some good questions though. Delores, take it away.
All right, thank you. I have the privilege of presenting on behalf of a team that has been assembled by NASA to do one of the things that Elizabeth Barnes says she was not going to do. So we're really all about anomaly detection. And we're trying to detect anomalies or unusual behavior in solar storms and storms that create space weather. So I am going to tell you that Hannah Marlowe is from Amazon Web Services, and she has been doing the heavy computing. Janet Kazira from NASA has been guiding the science, as have I, and then Liam Kilcommons has been doing the heavy data processing, of which there is a lot to get to a machine learning data set. So here we go. Let me tell you just a little bit about space weather in case you're not familiar with it. It's a national priority based on the Pro-SWIFT Act of 2020. We want to reduce our vulnerability in our power grids, in our aviation activity, in our communication activity, to sort of the vagaries of what the sun can do when it decides to behave badly. And when it does that, we generally put that into a couple, 3 categories. Solar flares you may have heard of, solar energetic particles, perhaps not. You may have heard of these bullets of material that the sun can episodically send towards Earth called coronal mass ejections. And we're going to try and determine from some really older data sets whether or not there's a change in the dynamics of the system when we're just experiencing fair space weather compared to really unusual space weather. So there are a number of ways that this can be applied. We are going to apply it to data that have been acquired in low Earth orbit for decades. We've got 1 decade in particular where we've got a particularly homogeneous set of data, and we are, even though it's homogeneous, we are realizing that there's lots of artifacts. So we are creating a machine learning ready data system, a data set, and then going after the anomaly detection via a random forest cut. So what is a space weather storm? Well, the sun is always sending out parts of its atmosphere because it's so hot into space, but episodically it throws off supersonic bullets of magnetized plasma. And when that magnetized plasma reaches Earth 1 to 2 days later, it interacts with our magnetic field. And if it has a certain orientation just opposite our dayside magnetic field, that allows a connection between this energized solar wind and the Earth's magnetic cover or its protection, and actually opens it up and allows energy to come in. One aspect of that, there are many that we're going to be looking at, as what happens when it is that so much energy comes in that it actually draws part of our atmosphere out. In that case, we tend to have oxygen ions being pulled out of the atmosphere. They can interact with the energy and the fields that are being generated and become part of materials that are actually shot back in to Earth's upper atmosphere. So some of these particles come screaming into the vicinity of Earth of 4 or 5 radii, and because of the configuration of the magnetic field, these particles are actually caused to drift around the Earth. They're ionized particles, so they create a current, and we can detect that current at Earth. So that current, that detection of that current is going to be one of our verification methods, because when that index is very negative, we know that a storm has occurred, and that we've known that kind of thing for about 160 years. What we're really after is, can we use space-based assets to look at the nature of the particles that are being shot in along the magnetic field lines from what we call the magnetotail. We call these precipitating particles, but they're not your typical rainstorm type of particles. They are charged high energy particles. So what might that look like? What have our eyes seen this as? Looking from below in the auroral zones, people who have been in the high latitudes have very typically seen these beautiful white and green aurora. Sometimes you'll actually get to see the red up above. This is indicative of the charged particles coming in and interacting with our atmosphere, knocking off particles, electrons, or maybe just putting them in an excited state. But the anomalous events are ones that cause great red aurora at very low latitudes. So to give you a sense for how far that might extend, the NOAA Space Weather Prediction Center has a storm scale that goes from 0 to 5, much like a hurricane scale. It says, fair weather, slightly disturbed, moderately disturbed, really disturbed. But it's open-ended, and sometimes we get these great red aurora at very low latitudes. There were about a dozen storms in the early 2000s, which are part of our data set. And then I've been working on the truly great auroral storms of the last 500 years. We only have one of these in one of the data sets if we can extend it. But we think we have enough information to extract information about whether or not the system dynamics are changing. We're going to use a low Earth orbit spacecraft. It's the Department of Defense's twin to the NOAA POES. Operates at about 850 kilometers, and it was always intended as its first purpose to sense clouds and tropospheric weather. It has a space weather component though, and those data have been taken since the 1980s when I was in graduate school. Since the 1990s, we've had a more uniform data set, and we're going to be looking at particles that have enough energy, 100 eV. So about 30 eV is what one particle needs to take an electron off of a standard upper atmosphere oxygen atom. So you can see that there are some very energetic particles that can have interesting effects. The data are taken at 1 second cadence over years and years. It means we have big data, but the extreme events are rare. So we're going after that with a machine learning process. And we're going to do anomaly detection. And one of the things we also want to know is, can this detection help us do some feature engineering, even find things that we might not have known about in the data set? So here's what it might look like. This is a day's worth of passes over the auroral zones, and then the satellite passes over the low latitudes and goes into the high latitudes of the opposite hemisphere. The particles that are coming in for this event, and I'm showing you a good case of an extreme storm, are particles that will make usually the green aurora. What's interesting about this event is that there are 10 to the 12th of these coming in per meter squared per second. That's 1 trillion particles raining down on a meter of the upper atmosphere. that's usually an indication that something's going on. We're not in fair weather. But more interesting to us is a data set that has been less used that looks at these softer, kinder, gentler, not quite, particles that come in at lower latitudes during extreme storms at about the same level of intensity. But if we put these two pictures together, our NASA colleagues have had the idea that they might tell us something we've not seen before. So we're going to use the channels of the particle detectors. There are 19 channels, each measuring particles at 1 second, lots, millions of data points per day. We are going to put these together. You see the spatial distribution here. Machine learning doesn't like gaps. The machine learning system wants to have these data all kind of in a uniform set, nicely spaced, cleaned up. And so we have put this entire data set, and actually several days more, from the 27th of October 2003 all the way to the 31st. We have essentially crammed these orbits all together. I'll show you that right down here. This is one of the aurora that was actually indicated as seen in southern Arizona. And so what we're seeing are the signatures of the typical green aurora, and then superimposed on that are the signatures of something very anomalous, kind of like, oh, this is hurricane level behavior. We do have to do quite a bit of pre-model data prep. Here is a multi-day signal of this, and you can probably by eye say, well, that looks unusual compared to this. And we want to train a system to say, yep, that's unusual. But there's a lot of residual noise. We have to put multiple orbits together to reduce the small scale sensitivity. We're removing residual noise with the median filter. We're actually determined that we can detect anomalies that are detector anomalies, and we put those over in a different bin. But of course, we had to then reprocess the data when we figured out that that was happening. Once we have our data nicely lined up, we're going to put it into a random cut forest method that Amazon Web Services has used to detect these outliers. And all right, here is our system all put together, and we have trained this random cut forest to detect anomalies. And the detection occurs, yes, indeed, when we're seeing these red aurora. We have other aspects of this that we're looking at. We've used about 3 years worth of data and then evaluated it on 4 years of data. And we've also looked at this with respect to that current index that helps us determine, hey, is that really a storm? So finally, our methodology, we have been looking at these anomaly scores and determining what is a true positive. It was a storm, it was an anomaly. What's really interesting are these events where they're either non-storms by ground-based standards, or there was a storm, but somehow or another the detector didn't find it. We're evaluating this with something called an F1 score that helps us determine whether or not we're really doing a decent job of this, and it's looking very promising. So I will simply close here by telling you that we are categorizing these kinds of patterns in these low Earth orbit data, and we're scoring them on whether or not they're a superstorm, merely an intense storm, or a fair weather storm. And as one might expect, a lot of the work, 80% of our work, has gone into the data preparation, but it has really told us so much about what's in our data. So I will be happy to take a question or wait till the end. Thank you.
Thank you, Dolores. Fascinating and beautiful. Great to see your work. Quick question from Slack. Reasons for selecting random forest, and a random forest cut is same as random forest.
The random forest cut, yeah, we did want to go in and with this huge amount of data, we thought that the best approach, and one that Amazon Web Services could support, was where we take these huge amounts of data and put them into small random chunks to look for these anomalies, and then we train on that. So it was a very definite intent to do that because we wanted to break this huge database down into a lot of small random units where the system could detect the anomalies and then train itself to assign the anomaly scores.
Great. Thank you, Dolores. And you have another question from Lander on Slack, but Eduardo Rodrigues from IBM, please load your presentation and take over. Thank you. Thank you, Dolores.
Hi, everyone. Can you see my screen?
Yes, see it well. We hear you well.
That's awesome. So thank you for attending this last presentation. I promise I will be quick. This is an extension we proposed to the dynamic mode decomposition method. This method is intended to project the observed data into linear dynamical system. For the atmospheric science community, this method is better known as linear inverse model. So I'm showing some the results here, but also, give a quick overview of the method. I think it's pretty interesting to show it. But just before doing that, let me contextualize a little bit what we are trying to achieve here, right? So there are these different time scales for weather and climate predictions that are around. So we have weather predictions, for instance, at IBM, we have in the weather company, we have these up to 15 days forecast, daily and hourly. We have also the seasonal, and actually many people do this as well, of course. But yeah, this typically is 3 to 9 months forecast. There are also long, not forecasts, but simulations to understand what would be the impact of climate warming, like the CNIP. But in between, there is this interest in the 110-year forecast that, it's common these days. You have seen much research being done on that area. Much is done in the physics-based simulations. We are not going that direction, right? So we are using data-driven methods I described here to make those predictions. But yeah, there are, as I said, many people doing these decadal forecasts. This is an example from NOAA for running this CM model in this forecast-oriented low ocean resolution. It's a forecast that, its name says, has lower resolution for the ocean, just 1 degree, but it's much higher resolution on the ground, on ground. And it's a huge simulation, as you can see from this slide here, right? So it's 15, 18 years of simulation per day. So it's something like 4,700 model a year runs. So it's really, really a large simulation. Another example is DeepO, run by NCAI. So it is very, very large also simulation. 62 distinct assembled members running 10 years. So, and 40 members. So it's really large simulations. There is a different approach that is based on DMD, the dynamic mode simulation, or the linear inverse model. This is not unprecedented. NOAA has done this in the past. Here on the left, you can see a screenshot of the website. We had these decadal link forecasts. And it is a very interesting method that I will describe briefly here. It's basically what the method does in the most basic form is to try to fit a model like you see here on the right. This first equation is a linear dynamical system in which we have this X state here. Think of it as every single point in a grid for each one of the variables. And you're just seeing it as a linear system, right? So we evolve it linearly through time. And the beauty of this is that it has an exact solution. So if you can fit a model like this, you would have an exact solution for your model. Of course, the system usually is not linear, the system itself, but if you assume it is, and if the nonlinear part is small enough, then this would be a good approximation. And then all the dynamics would be characterized by the eigenvalues and eigenvectors of A. So, of course, if you have for each point of grid one X here, one element of this vector X, that will be a huge matrix. So you wouldn't typically assemble that matrix, let alone computing eigenvalues and eigenvectors. But the method is a method, the DMD method is a method that actually uses dimensionality reduction to compute the leading eigenvalues and eigenvectors of these matrix. So it's much cheaper to run. So we can typically run these algorithms efficiently. So you would typically choose to just project the solution into the leading modes of this matrix. That's what it is typically done. So, and then everything would be linear, right? So again, the beauty of this is that the solution, as you can see here in this diagram, would be completely linear. You have the input X at time t that you project in this low dimensional space and then evolve it through time to compute the steps ahead, right? This would be the solution to the algorithm. And this diagram hinted us to try out some neural networks on that. If you naively would use this directly, that wouldn't be very smart, because if everything is linear, the solution here would just get you the solution you would have with the standard DMD. So there would be no use for gradient descent here. But what we are proposing here, it is an extension of the method to try to better approximate the solution of the nonlinear part of the equation. Let me try to describe that better here with this slide. So the standard procedure to use the DMD or the lean method would, as it is described here in this excerpt from this paper, right? So you have a dynamical equation, a differential equation describing your dynamics here, and you have a linear. You assume that it has a linear component and a nonlinear component. But usually when you try this method, what you do is let's assume that you can approximate the nonlinear part linearly as well. So that's precisely what this author is doing here. So the second equation highlighted in green here, you see that it's just an approximation of the nonlinear equation 1. And you could just apply the method as I briefly described previously. Here we are taking a different approach. So instead, we are trying to approximate the nonlinear part as a neural network, in a very special neural network. A neural network that's similar to ResNet, for those who are familiar with this network. And basically, the network has this a bypass. I will describe in the next slide what it is and what are the assumptions there. But here we have our network that has a bypass. The main path on top is just the regular solution from the DMD, but we add this bypass with some nodes which could approximate some nonlinear functions.
2 minutes.
But the beauty of this is that you can train it so that it could give the solution initially the same solution as the DMD, but it can learn different solutions that would approximate the nonlinear part. I will skip this. It's just to mention what the ResNet is and show you quickly some results. So here we have ACC for SSTs. On the left is the standard DMD. On the right is our proposition. And you can see that we achieve higher scores compared to the standard DMD, but also higher scores compared with the dynamical model, the CFS, with this 5-month lead time. We have also some comparisons in the paper I described in a point in a minute, but yeah, we have also run for longer lead times. For longer lead times, things get a little bit trickier, and I invite you to read the paper. And if you have some idea, we can discuss that. But basically, this is it. I have here the address for the paper that's on arXiv. If you are interested, it's an interesting method and an interesting extension, I think, that has some advantages and possibilities. So I think I run out of time, so I will be glad to answer any question that you might have.
Thank you very much, Eduardo. Another fascinating method that's tempting to test. Please all ask questions. We have very little time, but if you have a question for any of the speakers, put it in Slack. And Eduardo, like a general question, what's the degree of nonlinearity where your method becomes a difference maker?
I would say that the method is quite competitive with some mild nonlinearities. It's not supposed to try to address very large ones. We try out these with SSTs because it's low varying and it's a well-behaved variable, but I would guess that wouldn't be a good match, for instance, for a precipitation, for instance, that, it's way trickier to try to focus.
Okay, thanks. And a question from Slack, from session 10. Would it be possible to make ensemble forecasts from DMD or ResDMD?
Yeah, definitely. I think there are many possibilities to include some probabilistic and definitely applying ensemble forecast would be one possibility. And we are trying something a little bit different, more similar with the first presentation we had in this section, in which we were trying to match a distribution rather than a point forecast. I think that would be really promising, but definitely ensemble would be also a way to try to characterize the uncertainty.
Cool. Yeah, I encourage everybody to work with distribution. I think this is as AI is moving and getting more sophisticated, I think that's a good frontier for all of us to push. I'm going to add that Sudha has added in the Slack that they are working on an API. That's a great data set, great to access, and also potential research there. And then otherwise, we're getting really close to the end. I'm going to share before the session started, we asked, when is it a good time and where should you look for Aurora Borealis? And I'm going to share with everybody the advice. So you should go to Fairbanks during one of the equinox because it's not too cold, not too, well, it's not going to be too warm there. But I think this is our panel's recommendation for everybody. Otherwise, I thank everybody for attending our session, and all speakers. Please keep on interacting. We have some good interactions now in the Slack. Keep on going. And goodbye, everybody. And there's a poster session that is starting right now.